4.2 is log functions. So logs were actually invented to be able to find weird exponents. So we're going to work a lot with we can figure out the exponent, and that's how we solve a log. But there's also when you can't figure out the exponent for something like 2 to the x is equal to 6. You could do a lot of guessing and checking and come up with some weird decimal exponent that's going to get you really, really, really close to 6. But mathematicians spent a lot of time and created tables that were in the back of textbooks a long time ago before we had calculators that would do it for us to figure out those random missing exponents. So what we're going to work on today is more of, do you understand how logs and exponentials are related? Can you go from a log to an exponential? Can you figure out missing exponents? Kind of the same way we did in that exponential lesson in the previous lesson. And then by the end of chapter 4, we will talk about how in some situations we just have to use our calculator and get the weird decimal. All right, so again, logs are the inverse of an exponential. They were created to find exponents. All right, so some rules about logs. When you have the basic log function, this is read y equals log base b of x. So the x, the argument, the guts of the log, has to be a positive number. The base has to be a positive number. And it cannot be 1. So because when I write it in exponential form, a base of 1 isn't going to be exponential. A base of negative, like we talked about in the previous video, is going to make you be positive, negative, positive, negative. So it's not going to be a function. And then what you're taking log of can't be negative because you're not going to be able to take something and raise it to a power and magically get a negative answer. All right, so those are the rules for a log. The base has to be positive. The argument has to be positive. The base also cannot be 1. All right. So to go back and forth from log to exponential form, I gave you again what the log form looks like and the exponential form looks like and kind of color coded it. But then there's also this loop trick that a lot of people just memorize. So honestly, it's the base raised to the answer equals the guts. That's how you turn it into exponential. Or if it's exponential, it's log base, the base of the answer equals the exponents because logs find exponents. So the base stays the base when you switch from one form to the other. The answer of the log is the exponent of the exponential. The answer of the exponential is the guts of the log. All right, so we're going to do some examples of switching. Hopefully that'll make some sense. All right, so again, the base is 5, so the base will be 5. Raise it to the answer. It should equal the guts. So 5 squared is equal to 25. All right, this one's log base 7. So in exponential form, it'll be 7 raised to the third is equal to x. And then this one, the base is 4. So 4 raised to the answer equals the argument. So 4 to the y is equal to 26. All right, so going the other way. I think there's another one coming. Bless me, sorry. Excuse me. All right. Going the other way. If it's an exponential form, the base is what's being raised to a power. So it will be log base 2. That's like a little subscript. It should be under and small. So base, log base 2 of x equals 5. Because remember, logs have to equal an exponent. So this one would be log base b of the answer equals the exponent. So of 27 is equal to 3. This last one, it's log base e of the answer is equal to the exponent. So log base e of 33 is equal to y. And if you remember learning this in Algebra 2, you should remember that log base e gets a special notation. We call it ln. Instead of writing log base e, that's the natural log, and it's ln. And that'll be on a slide coming up that you can write all that down. All right, so if they ask you to evaluate a log, that means that no calculator necessary, that you are only looking to write it in exponential form, figure out the exponent. They're giving you something where you can figure out the exponent. So we're really doing what we did in 4.1. We're going to write it in exponential form, and then it's nothing new. All right, so I'm going to say this is equal to x. And then another thing that hopefully you remember from Algebra 2, if there's no base written, it's assumed to be 10. It's called the common log. Again, that'll be on a slide coming up, so you can write all that down. All right, so when I write it in exponential form, it'll be 10 to the x is equal to 100. So then you just have to be able to say, we know that 100 is 10 squared, so x must be 2. So our answer is 2. Log base 10 of 100 is 2. And up here, make sure you read this. You have to show work on a test. So even though this is pretty obvious that it's 2, once you understand the concept, you have to show work or they won't let me give you your points. All right, so again, say this is equal to x or y or whatever, a smiley face, some variable. Write it in exponential form. Base raised to the answer equals the argument. All right, and then we've got to think about what's going on here. So I know that 125 is 5 to the third. I also know that to get it out of the denominator, I can make it a negative exponent. So then x must be negative 3. All right, so for the next one, same concept, say that it equals x. Write it in exponential form. And then make the bases match so we can use that property we learned in 4.1. So remember 36 is 6 squared. And remember that this is like an understood 1. So now we're saying 2x is equal to 1. So x is 1/2. Now again, I know once you wrote it like this and you're thinking, oh, I can just square root 36. And then if you remember square root is an exponent of 1/2, you could jump to the correct answer, but you must show work on a test and they're expecting to see a process like what I just showed you. All right, so here's that slide I was telling you about, common log and natural log. So if there is no base written, then you don't, then it's assumed to be a 10. Sorry, I'm trying to multitask. I just got a text. I'll pause and that actually make this make sense. All right, so a common log is when the base is 10 and we don't write the 10. We just leave the base off. So no base we assume is a base 10. It's called a common log. It's called that because we have a base 10 number system in America. That's where the common log came from. The base 10 number system is in most places. There are some that have more than that. Fun fact, we have a base 10 system because we have 10 fingers. So we can count to 10 with our hands. A natural log is when you have base E. I'm really not sure where natural came from. I'm not 100% sure on why I got the name natural log. But anyway, that's what it's called. And we don't write the E. We actually don't even write the whole log. We just write LN for natural log. And it was created by somebody that does things like backwards of how we say things in America. So that's why it's LN and not NL. But anyway, LN means natural log. We assume a base of E. And remember that E is a roughly 2.7, but it's a button on your calculator. All right. So we're going to do a couple of things with just some basic properties. We'll get lots more properties in 4.3. These are just basic ideas that are really like, once you understand the concept, like common sense. So anytime the base and the argument match, the answer is 1 because b to the what is b. It has to be 1. So like down here for this one, 9 to what power is 9? Well, obviously 9 to the first is what's going to work there. All right, the next one is anytime the argument is 1, the exponent had to have been 0. So log base anything of 1 will always equal 0 because 0 is the exponent that gives 1 as an answer. So again, down here, if we're thinking 8 to what power is 1, well, the exponent that gives us 1 as an answer is 0. So we have an answer of 0. All right, so the next set is some more properties, and again, they're kind of like no-brainers once you understand the concept. If the bases match, then the exponent is the exponent. Like that should make some sense. Like b to what power is b to the x? Well, x has to equal x. So here, if we say 7 to what power is 7 to the 8th, well, then x must be 8. So anytime the bases match, that exponent is the answer. Here it's writing it the other way, like this is actually exponential form that includes a log, but still, as long as those bases match, the extra number is the answer. So if I write this in log form, so if I say it equals x, so it'll be log base 3 of x equals log base 3 of 5, then it should make sense that x must be 5, because as log base 3 is the same on both sides. All right. So those are those two basic concepts. All right, so solving log equations. Again, we will do more log equations another day. We did a few of the exponentials that were the basic kind where if you can make the bases match, then the exponents have to match. Well, in this lesson, we're going to do a few basic logs where there's only one log in the problem, because those are easy to solve. Once we have learned some properties, then in a previous, sorry, not previous, that's the wrong word, in a future lesson, we're going to see how we can solve more complicated log equations and more complicated exponentials. But for now, it's just the basic ones where there's only one log. So you're going to write it in exponential form and then solve whatever equation you got. So with logs, these are another one where we're going to create some answers that may not work. So you have to check your answers to log equations on a test. Like make a note of that. Make sure you file it in your memory. You have to check answers on a test for logs. And what we're looking for is that it works all the way out when we check it. And we'll do some more extensive checking when we do the future lesson with more complicated logs. For now, we're really just going to think if the base of the log is 0 or negative, or if the number inside the log, the argument, guts, is negative, then it's a no-go. Those are the kinds of things we're looking for to say, no, that answer is no good. All right, so write it in exponential form. This one will become 7 to the third is equal to x. And then we just need to know what 7 to the third is. It is 343. So our answer is 343. Before you box it, just make sure, yes, if I plug 343 in there, that looks fine. It doesn't break any of the rules that we have up here. All right, so number 15, we're going to say x squared is equal to 64. Base to the answer equals the guts. And then we're just solving using some skills we already know. We know to take the square root of both sides. So then we would get x is equal to plus or minus 8. Well, if we keep these guys in mind, it can be positive 8, that's fine, but negative 8 is not going to work because you can't have a base that is negative. So we're going to say x is equal to 8 and box that. All right, so 16 is a lot like 15. It's just we have to remember how to simplify a radical. So we've got x squared equals 75. We take the square root of both sides, then we will get plus or minus the square root of 75. But we also have to break that down. So remember 75, we can break it down to 25 times 3. So then we would get 5 root 3 as our simplified version. And then again, just like 15, the negative is no good because the base can't be negative. So we'll box 5 root 3 as our answer. All right, so for 17, we're going to say x to the negative 2/3 is equal to 1 over 49. All right, so remember when we have a fraction exponent, we learned to raise both sides to the reciprocal. Since it's negative, I'm going to keep it negative, so raise it to the negative 3/2. All right, so then we get just x, and let's make myself a little more space. Because it's negative, I'm going to flip it and make it 49 to the positive 3/2. And then we're going to remember that an exponent, an exponent that's a fraction, the denominator is the root, so this will be the square root of 49, and the numerator is the exponent. So the square root of 49 to the third. The square root of 49 is plus or minus 7. And then to the third, and we just said 7 to the third up there was 343. Is that correct? That was 7 to the third, right? Yeah. All right, so again, your base can't be negative, so we just want 343. All right, so 18, write it in exponential form. So you get 3 squared is equal to 4x minus 7. So then 9 is equal to 4x minus 7. So then add 7 to both sides. Divide by 4 on both sides. We get x is equal to 4, and that shouldn't cause a problem. These are the kind you're going to have on your test, I think. So I haven't seen what the new tests look like, but in the past they have. So if I'm going to check on a test, then it's going to be something like this is what they're looking to see. So we can say 16 minus 7, so 9. And then 3 squared equals 9. So check, we're right. So that's what they want to see for a check. This was the first one that resembles something that I think is going to be on your test. The other ones are to make sure you can handle Math Excel. All right, so that's why I only showed you checking that one. The rest of them, you would really just write it in there and be like, you can't have a base that's negative. Nope. All right, so 19, writing this in exponential form, it'd be 4 to the third is equal to x squared minus 9. 4 to the third is 64. Add 9 to both sides. So that's going to become 73. Take the square root to both sides to get rid of the square. So x is plus or minus the square root of 73, but I'm double checking my math because I'm just curious and making sure I didn't make a mistake. All right, 73 is a prime number, so it'll just be plus or minus root 73. And then before you stop and say we've been throwing out the negatives, make sure you look back at the problem. You're going to plug it in here and immediately square it. So it doesn't matter if it's positive or negative, it's going to be positive. So it'll be root 73. The square root of 73 is actually going to be less than 9 though, right? Okay, I'll show the check on this one because I want you to understand what I'm talking through here. So log base 4, if we do root 73 squared minus 9 is equal to 3, then we're saying log base 4 of 73 minus 9 is equal to 3. Oh, see, I'm glad I wrote that down because I was talking you into something that made no sense. Because if you square a square root, you get the whole 73. We're not actually taking the square root of that number, which is what I was trying to say a minute ago. Sorry if I confused you. So this is going to be log base 4 of 64 is equal to 3. 4 to the third is 64, so it works. And then the only thing that changes if we make it negative is there's a negative here. But if I square a negative, I get a positive. So this is all going to stay the same. So that means that the positive and negative will both work here. All right, so next we have graphing. All right, so remember logs and inverses, logs and exponentials are inverses of each other. That means that you can graph a log by reversing the coordinates of an exponential, and they should be reflections of each other over the line y equals x. So this first time I'm going to graph an exponential and a log to kind of drive home the point of what's in that paragraph. And then beyond that, I'm going to show you what needs to be done on a test. All right, so if I graph this, then remember we said with an exponential, we can just do -1, 0, 1. If we put -1 in, it's going to flip it and make it 1/3. Put in 0, you get 1. Put in 1, you get 3. So -1, 1/3, 0, 1, 1, 3. These guys hug the x-axis and either shoot way up or down on the y. So it would have a domain of all real numbers and a range of start real close to 0, but don't be 0 to infinity. And this particular one is always increasing. All right, so I went through that kind of fast, but hopefully you've got a handle on 4.1 and you are okay with graphing those. All right, for a log, remember that since they're inverses, we can just switch x and y. So this would be 1/3 because they have the same base. Okay. Or if you wrote it as 3 to the y is equal to x, I think of this as y. Then you would be plugging in -1, 0, and 1 for y and finding x values, which does just flip-flop your table. It switches x and y, which is how inverses work. All right, so then we have a point at 1/3, -1, 1, 0, and 3, 1. So this one is going to hug the y-axis, and it's going to go off towards the x's. All right, so that's still increasing, but the domain is now restricted from 0 to infinity, and the range can be all real numbers. Since the x and y switched, the domain and range also switched. And then if we draw in the line y equals x, you should notice that they are reflections of each other over that line. All right, so using the idea that we know those are inverses and how that works, what we're going to do to get a graph of a log is we're going to write it in exponential form. We're going to make a table where we plug in -1, 0, and 1 for y and find x values. So remember, -1 is just going to be the reciprocal of 5, so 1/5. To the 0 will be 1, to the first will be 5. Log graphs are going to look a lot like one of those 4 pictures of exponentials that we did, but they're always going to hug the y-axis because the y-axis is now their asymptote, which I needed to go back up here and write that. So for an exponential, you have a horizontal asymptote that is usually x is equal to 0. Y is equal to 0, sorry. It is the x-axis, but the line y equals 0. For a log function, you're going to have a vertical asymptote, which is the y-axis, but the equation x is equal to 0. All right, if you're asked about that in Math Excel, then there you go. I don't think on a test that they're going to ask for the asymptote. They haven't in the past, but they may surprise me this year with their changes. All right, so we do 1/5 -1, and then 1, 0, and then 5, 1. Then we're gonna hug the y-axis. That should have gotten closer to it, not farther away. On your graphs, we're not looking for perfection, but don't cross the y-axis. Try not to touch the y-axis and make sure you're getting closer to it. and that you actually go through your points. All right, so then domain, range, and whether it's increasing or decreasing. Okay, those are the things they're going to ask in Math Excel. So for a log function, the range will always be all real numbers. The domain is going to depend on where your asymptote is. So if there's nothing extra, if it's just a basic log, then it's going to be 0 to infinity. If it's a negative log and it reflects, that's going to reflect it, then it would be negative infinity up to over to 0, not up to because it's the x's. But anyway, you get the idea. It's going to be a 0 and an infinity for domain, unless we start shifting things. The range will always be all real numbers. And then remember, for increasing, decreasing, we go left to right. So if you start at the left and draw the picture, it's going up fast and then up slow. So it is always increasing. So negative infinity to infinity. It'll always be this, but you got to decide, is it increasing or decreasing? All right, so number 21, there's an extra number. So to start with, we're going to ignore that plus 3. We're going to make a table that says 2 to what power gives me x. And we're going to make our table. So plug in -1, 0, and 1 for y. So you'll get 1/2, 1, and 2. 2 to the -1 is 1/2, 2 to the 0 is 1, 2 to the first is 2. And then we'll say that this, it's on the outside, so it affects the y's, so it's going to move us up 3. So we will add 3 to our y's and get a new table. So these will stay what they are, the x's. The y's will become 2, 3, and 4. So when I plot my points, I have 1/2, 2. I have 1, 3, and I have 2, 4. And again, like that almost looks like it could make a line, but remember a log function looks like this. So it could flip and go this way. It could flip and go this way or this way. Like those are kind of the options. So it's always going to hug the x-axis unless we shift it left or right, and that moves the asymptote. And then this one is going to try to start leveling off. All right, it probably should level off more than I just did that one. They tend to be a little flatter. So something more like that. All right, so domain is still going to be 0 to infinity. The range is always infinity to infinity. This one is going up from left to right. So we are increasing negative infinity to infinity. All right, so just for kicks, let me just show you this. If this was a negative right here, actually, let's go back up to the top one because there's more going on there. If this had a negative right here, then what would happen would be that these would be the same, but they would all be negative. And so your graph would look like this. And so that would change the domain to be negative infinity up to 0. No, it wouldn't because we're talking about x's. Sorry, mercy. We were talking about y's, it would be, but the domain is the x's, so it would still be 0 to infinity. And it would change to decreasing. All right, the other thing that could change it is if we had a negative in here, that would do what I was thinking. That's going to, so it'd be negative. It would still be, so you'd have to like divide by a negative. And so it'd be -5 to the y. So we would still be getting negatives and it would still make the same graph. So never mind about that. Okay, so moving on to number 22. All right, so number 22, remember that Ln is base E. So when we write it, we're saying E to the y is equal to x because we're only going to worry ourselves with this. So we're going to ignore the extra for now. So when we make our table, we'll say -1, 0, and 1. We know that the 0 is 1. So the first is going to be roughly 2.7. So the -1 is going to be a little less than a half. Let me put it in my calculator and make sure. Let's see. We want 1 divided by E, and we get 0.3678 yuckity yuckity yuckity. So we're just going to round that and say it's roughly 0.4. All right, so we are going to make the change of, let's go right to, remember if it's on the inside, it goes left or right, and it does the opposite of what you think. So that means we're going to add 2 to our x's to get the table we're going to plot. So it'll be 2.4, -1, 3, 0, and 4.71. 2.4, -1, 3, 0, and 4.71. So if we shift everything to the right too, that means we're also shifting this asymptote that was the x-axis. It is now shifting to the line y equals 2. So when I draw this in, I need to be careful to not pass up that spot on the x-axis. So we would have a domain of 2 to infinity, because we moved our asymptote to 2, a range of -infinity to infinity, and then we are always increasing, so we would say increasing from -infinity to infinity. All right, so again, in Math Excel, make sure you choose the log graph, so the one that looks like this. Put a point at 1, 0, and then a box is going to pop up, and you're going to change it. Now, pay attention. If it's an Ln, it's going to give you a base of 10. Anything else is probably going to give you base E. So don't get locked into, ooh, they give me base E. When it needs to be base E, they're going to give you a different base. So always go change the base. So remember, if it's Ln, you put in an E. If you are doing this problem, the base is 2. If they give you a log with no base, then remember it's a base 10. This one was a base 5. So first thing, once that box pops up, is change the base to the base in your problem. And then if there's some kind of shift that happened, make sure that you make that change. So this one, we went to the right. So that was a horizontal shift, +2. So you'll do a horizontal shift and you'll put in a +2. For this one, we went up 3. So that's a vertical shift. So in the vertical shift box, you would put a +3. If it was a -3, then you would put a -3. Or if they give you one of these and it says x plus 2, then remember you would go left 2. So it'd be a horizontal shift, -2. All right. That is all. If you have questions, let me know. Sorry for the misspoken things that happened in the middle of this video. All right, this is actually going to cover 4.2a and 4.2b. You should be able to do both of those with this video. Again, if you have questions, please ask. You can email me with questions if you need to while you're at home.